So far we have seen several models for aggregate planning. We started with the tabular method, then we looked at the linear programming or LP based algorithm. We then did the transportation based algorithm, and we also did a dynamic programming based algorithm. The tabular method was an evaluative algorithm where the user inputs the values of the production quantities and the workforce as relevant, and the tabular method would evaluate a total cost function, and the user could vary these values and try and locally optimize the total cost. The linear programming based formulation actually considered a maximum of 8 different costs, which kind of occurred in 4 pairs: regular time and overtime costs, inventory and shortage costs, hiring and laying off costs, outsourcing and underutilization costs, and then there were a variety of constraints. The transportation based algorithm was essentially solving a certain restricted version of the linear programming. The transportation model did not consider variable workforce, but we showed that it could consider the 6 remaining costs and then solve it. The dynamic programming based algorithm, in the DP algorithm we introduced a new idea that if there is production then there is a setup. So there was a definite setup function or a setup cost whenever there was production. Now all 4 of them have something in common, which is that in all 4 models the cost was linear or proportional. For example, in the tabular method, if we said that it is going to cost 100 rupees to produce an item on regular time, then we said it would cost 200 rupees for 2 items, or if certain x number of items or man hours are utilized and it costs 100, then the total cost will be 100 into x. So the same linearity or proportionality was used across all 4 of them. Even in the DP based algorithm, we said that if there is an inventory cost of carrying a unit from one period to another, if x units are carried, then the total inventory cost will be x into the number of the x into the cost of carrying a unit from one period to another. So there was this linearity or proportionality in all of these. Let me just write only the objective function of the LP algorithm and also try and show the linearity there. So in the linear programming formulation, the objective was to minimize sum of, we used a certain notation, we used R into RT plus O into OT plus I into IT plus S into ST plus H into HT plus L into LT plus into outsource of T plus U into UT. We had used 8 costs in the objective function, and the objective function was to minimize the sum of the 8 costs. The lowercase alphabet represents the unit cost, and the uppercase represents the variable. So if capital R T is the number of regular time man hours used and small r is the cost per man hour per period, then the total cost of regular time is equal to R into RT summation over T equal to 1 to T for all periods. We could consider that this R is constant across all periods, we could have this R changing across all periods, and if it changes then we would add a small subscript RT which says this is the regular time cost in period T. but if this cost is going to be the same across all periods, then we will use this. Similarly, we used all these values. Now obviously, when we have to solve this linear programming problem, it is necessary to know the values of R, O, I, S, H, L, out and U, and these will have to be provided by the organization for whom or for which an aggregate plan is being made. Now let us ask ourselves two things. Let us first try and question the linearity assumption in the objective function, and then let us also ask a question as to how does one go about finding out or computing the actual values of these coefficients. It is only customary to say that if we want to find out this R, which is the cost of regular time production, which means cost per man hour of regular time, how does an organization compute this value? There are many ways by which they can do it, but the most common way is to find out what are all the components of the regular time cost. Now in this model we have not explicitly used the operator payroll, so we assume that the payroll also is part of this R, the salary to the operator who is working, plus it will have certain raw material cost, plus it will have some cost of consumable and so on. So all these components of this cost are now listed, and then one goes back to earlier periods, say the last 6 months or the last 1 year, and then we can compute the total money spent on regular time production on each of the components of the regular time cost, and then add them to get the total regular time production cost incurred over the last 5 or 6 periods, say. And then when we divide it by the actual quantity or man hours employed in regular time production, then we would get this R. Similarly, we would get this O, where all the components of the overtime cost are listed, and then they are evaluated or computed, and then that total cost divided by the number of man hours used in overtime would give us this O, which is the per period per man hour cost for overtime. Like this one can go about, or one usually goes about, trying to compute all these costs. Maybe the easiest would be the outsourcing cost, assuming that this entire product is outsourced, so finding the outsourcing cost would be relatively easy. Inventory cost would be reasonably easy if the inventory cost is dominated by the interest on borrowed capital. If we are going to use other components of inventory cost, such as cost of space, cost of power, electricity and other resources, cost of manpower, cost of special facilities, then this I would have the largely dominated by the interest on borrowed capital or the interest rate, and then the other costs associated with space, people, facilities, etc. will have to be added. Now computing this S is not easy, because any shortage or back order cost will have an important component, which is eventual loss of customer goodwill by not delivering things in time and by back ordering. So that cost is not easy to compute. Similarly, the cost of underutilization, though computable, is relatively difficult, because this is the cost of keeping a facility idle or keeping a man hour of resource idle. So it also has to be computed carefully. H and L are cost of hiring and layoff, which can be calculated reasonably well. At the end of it, the point that I wish to make is that it usually, for any of these 8 costs, the common practice is to go back in time and find out what was actually spent under these costs, or whatever expenditure could qualify under this head of, say, either a hiring cost or an outsourcing cost or an overtime cost, and then divide it by the number of man hours that has been used under that to get this. Therefore, it would be difficult to have an RT and say that if we are looking 12 periods, it would be difficult actually to give 12 different values and say that regular time cost was so much in the first period, so much in the second period, and so on. So it is customary to use the same value of R across all 12 periods. And because of the way the R has been computed, we are forced to use the linearity or proportionality, saying that if this is a per man hour regular time cost, and if RT man hours are being used, then R into RT is my total regular time cost. But in practice, we also know that every cost, particularly in production related situations, there is a fixed component and then there is a variable component. So if we start writing this R itself as having two components, something of the form say R naught plus R1 into R of t. If this R is of this component, which means there is a fixed cost R0 and then there is a variable cost per man hour used, then which is a very common occurrence, because the organization has certain fixed costs which can be apportioned to each of these costs. So if we start defining this R itself as a fixed cost having a fixed component and a variable component, then this will become R naught plus R1 into RT multiplied by RT. So this will become quadratic in nature. So if each of these costs has a fixed component and a variable component, then the linearity assumption is questionable and we may have to use a model which is quadratic in nature. Perhaps the other disadvantage of the linear formulation, the advantage of the linear formulation lies in its simplicity, easy to formulate, proportionality constraint is accepted and additivity is also accepted. Methodology wise, the simplex algorithm is well known and it is easy to solve the linear programming problem. But then when we computed this R and O and I and S, if in reality this R had a fixed component and a variable component, but for the purpose of computation and for the ease of computation, we have simply used one particular R which represents that R naught plus R1, then it is likely that there could be an error in the computation of R, and then the linear programming solution can sometimes give even a higher cost than what is actually incurred by the organization. Because the cost that is actually incurred by the organization has a fixed component and the variable component, but then we have approximated it to a single number R. So while the advantage of linear programming technique is its simplicity, ease of modeling and ease of solution, the disadvantage is perhaps its inability to actually capture the reality, because in reality costs have a fixed component and a variable component. So considering this in mind, some authors proposed a quadratic model. So a quadratic model for for aggregate planning is quite famous. It is also called the HMMS model, named after 4 researchers who are the authors of this work. Stands for Holt, Muth, Modigliani and Simon. So it is called the HMMS model. We will not get into the full details of the HMMS model, but I would possibly write down only the objective function and then explain how the HMMS model actually works. So the HMMS model, the objective function would be minimize So, the objective function has several costs. First, the variables. Wt is the workforce employed in period t, Pt is the number of hours of production in man hours in period t. W also can be written in terms of man hours, production man hours, workforce man hours, and IT is the inventory at the end of period t, which could also be written in terms of man hours. So, there are three sets of decision variables, a certain variables for the workforce, certain variable for the production, and variable for inventory. Now, the objective function is made out of several costs. Now, one is it has regular time payroll cost. This is like regular time payroll cost. There is a fixed component and a variable component. Now, there is a overtime cost, there is an inventory cost, and then there is a workforce changeover cost. So, this is the inventory cost, this is the workforce changeover cost, and this is the overtime cost. This is the overtime cost expanded in a certain form. So, now you realize that this portion is regular time payroll cost, there is a fixed cost and a variable cost. This is the typical inventory cost. In this model, shortages or back orders are not allowed. So, IT minus I star, there is an ideal inventory that is defined, and IT minus I star the whole square is the penalty, and that is multiplied by a C8. Now, here again there is a workforce changeover cost between Wt and Wt minus 1 and C12 whole square. Now, these are other costs that relate production and workforce. So, they would represent the overtime payroll cost and so on. Now, we are not going to go into too much of detail. This is only one form of the objective function which is kept here. It is not absolutely necessary that the objective function has to be this. This is one form of the objective function, and this objective function shows a quadratic objective function. The quadratic comes from this, comes from here, as well as comes from here. It is not linear anymore. So, now there is a quadratic objective function subject to a set of linear constraints. This is the standard constraint that relates production, inventory, and demand. dt is the demand in period t in terms of man hours. IT is the inventory at the end of period t. IT minus 1 is inventory at the end of period t minus 1, which is inventory at the beginning of period t. This is production in period t, this is demand in period t. So, this is typically the inventory balance constraint. So, now we have a quadratic objective function. Let me again repeat and indicate that it is not absolutely necessary that this has to be the objective function. A quadratic model suitably defined for a specific organization may include additional costs also, or may leave out certain costs also, may include back order, which is not included in this function, may include outsourcing, which is not included in this function, and so on. This is only a representative quadratic function, where some of these costs are shown as quadratic functions of the decision variables, which are essentially Pt, Wt, and It. So, one may look at other objective functions also, but the objective function is quadratic, the constraints are linear, and then we have a non-negativity restrictions on the variables. So, this becomes a quadratic programming problem, which can be solved in many ways. A popular way is to actually, one could think in terms of taking this constraint into the objective function using a Lagrangian multiplier, and then one could solve. The other one that is right now associated here is quite simple in the sense that we have a quadratic function. So, the fundamental principle of a quadratic optimization problem is that the first derivative of a quadratic function is a linear function. So, one can differentiate this with respect to the variables. At the same time, one should be able to capture the dependency of the variables. The dependency of the variables are here. So, even though we have Pt, Wt, and It as variables, there is a relationship between Pt and It which is given here. So, it is possible to eliminate one of the variables through this constraint and then differentiate with respect to the other variables and solve it. So, when we differentiate, we will get a linear function involving Pt and Wt. We also have equations here. Differentiation would also give us a set of equations. So, finally what will happen is, on differentiation and inclusion of this constraint, we will have a set of linear equations to solve. Now, as we proceed, we may have some more variables than the number of equations. The reason being, these it minus 1 and it as well as wt minus 1 and wt would sometimes create more variables than the number of equations. In such cases, we define some initial conditions as well as some final conditions that we want, so that we make the number of variables equal to the number of equations and then solve a set of equations to get the optimum values of Pt, Wt and then it from them using this relationship. So, the primary purpose of doing the quadratic model is only to inform or indicate the need to consider a quadratic objective function, because though linear optimization and linear program and linear model is very simple to model, it is easy to solve. It has the difficulty that these coefficients, there can be some kind of an approximation in these coefficients, because of which even though we solve the LP optimally, the solution may not reflect what actually happens, because in reality the costs are not linear. So, if you want to capture that, then we can bring it into a quadratic model with a suitably defined objective function, and then I have explained broadly the methodology to solve a quadratic optimization problem. So, in terms of methodology, solution methodology, this is a little difficult compared to this, but this can give results which are little closer to what is happening, because in practice costs have a fixed component and a variable component, and therefore can result in quadratic optimization problems. Now, let us look at some more aspects of aggregate planning before we go to the next topic. If we look at the costs that we wrote 8 different costs. So, let me consider 2 of those costs here. One is the inventory cost and the other is the shortage cost. The other pair is hiring and layoff, and then of course regular time, overtime and outsourcing and underutilization. Now, let us consider a simple situation where the demands are 2500, 3000, 4000 in 3 periods. Now, in a typical aggregate planning problem, we are now going to find out what is this P, how much of production man hours are we going to use in these 3 periods, such that we minimize the total cost. Now P actually has 2 components, which is regular time production and overtime production, and we could use outsourcing. There are 3 things by which we can actually produce. Now, the total demand is 9500 over 3 periods. Now, we could do 2 things. One is, we can produce exactly 2500 in this month, produce 3000 in this month, produce 4000 in this month. If we are able to do that, it means there is going to be no inventory or shortage at the end of this period. Alternately, we could do For example, the total is 9500. So, let us say we could produce about 3200 here, 3200 here and 3100 here, or 3100, 3200, 3200, which means we are trying to keep the production quantities same, which is roughly the average of the demand. Now, if we do that, the production quantities are the same, but there will be inventory at the end of this period and inventory at the end of the other period. Sometimes there could even be shortages. For example, if the 4000 were here and the 2500 were there, then initially there will be a shortage or a back order. So, by making the production quantities equal in all the periods, we would incur inventory and shortage, and therefore inventory and shortage costs will dominate in the cost of the aggregate plan. So, that is one type of strategy to keep the production constant. Now, to keep the production constant implies that the number of people who are employed, the workforce, is also kept constant. But on the other hand, if we produce 2500, 3000 and 4000 every month, which means we are varying the production quantity, which means we are varying the workforce, which means we will incur hiring and laying off costs, but we will not incur inventory and shortage costs. That is another strategy. So, organizations can use either of these pure strategies, which is one of the pure strategy is to produce an equal quantity, incur inventory and shortage, keep the workforce fixed. The other pure strategy would be to produce the demand, vary the workforce and do not incur inventory or shortage costs. Otherwise, the organization can also look at what is called a mixed strategy, where we have a combination of pure strategy as both the pure strategies. Sometimes we can adjust or increase the workforce, produce more, hold inventory and so on. So, the problem which included all the 8 costs, the linear programming problem, was essentially trying to identify the best mixed strategy. So, one is the strategy employed, a mixed strategy. Can we use a mixed strategy and solve it? The other is sometimes there can be limits or constraints of these, which would also make a pure strategy not doable. For example, in this month the demand is 4000. Now, if we are following a pure strategy where we vary the workforce and we want to produce a 4000 here, suppose the regular time production capacity is only 2000 or 3000, let us say, the overtime production capacity is 500, then it would force us to go for outsourcing for another 500 here. Suppose the regular time production capacity is 2000, there is a 1000 capacity, there is a 500 capacity, then only 3500 is the maximum that we can reach here. So, we cannot follow the pure strategy. It also means that somewhere here we have to produce, store the inventory and then use it for subsequent periods, so that we can meet the demand of the subsequent periods. So, if we look at this, things that we want to do are, or things that we can play around are, one is to consider the pure strategies. The other is to adjust the capacities Now, somewhere in the discussion I mentioned that the regular time capacity, if it is 2000, let us say, then it will be 2000 in all these months. But can we adjust this regular time capacity during peak periods by hiring additional workforce? One of the models that we saw in the tabular method did exactly that. So, one is adjust the capacities by adjusting the workforce, adjust the capacities by overtime and outsourcing. So, all these are strategies that organizations use to meet the demand particularly if the demand shows a lot of variation. Otherwise, organizations will have to go towards outsourcing, and it might be difficult to get the entire product outsourced. Certain critical operations sometimes is outsourced, sometimes common operations are outsourced while the critical operations are done in house, so that certain capacity is saved by outsourcing this. So, outsourcing can happen in more than one way. Most of the times the entire product cannot be outsourced, only a certain part of it is outsourced. So, to that extent that capacity can be saved and used under regular time capacity or under overtime capacity. So, organizations look at all of these: variable workforce, variable or flexible overtimes, sometimes an extra shift, sometimes an extra day, and a combination of these two, a bit of outsourcing. All these are integral part of aggregate planning to try and get as much capacity as possible to meet the demand, particularly if the demands are fluctuating. Now, another important thing that is being done is what is called demand planning. Now, when we worked out the aggregate production plan, we assume that these demands are known and these demands cannot be changed. So, we have to meet this 2500 in month 1, 3000 in month 2 and 4000 in month 3. Now, let us try and work out some costs for this and see what we do. Now, we assume that the regular time capacity is 3000 per month. Let us assume the overtime capacity is 1000 and any number can be outsourced. So, now the best way to try and meet this 2500, 3000 and 4000, we will also assume that regular time cost is 100. We will say RT cost is 100, OT cost is 120, and outsourcing cost is higher than this. So, what we will do is we will have to try and meet. Now, we will also assume some here that the overtime capacity is 500. So, that to meet this 4000 we will use the 3000 regular time and 500 overtime. To meet this 3000 we will use 3000 regular time. Now, for this 2500 we will produce 3000 regular time and have an inventory of 500. Let us say here also we carry an inventory of 500. So, the total cost associated with this plan will be 9000 into regular time cost of 100 is 900,000. This 500 overtime would cost us 500 into 120, which is 60,000, and this inventory is 1000 units. 500 is carried here, 500 is carried here. Suppose we say that the inventory carrying cost is 10 rupees per period, there is another 10,000. So, we have a cost of 970,000 for this. Now, if unit price is 150 rupees, the unit price is 150 rupees, then the total money or profit or sale will be 150 into 9,500, which would give us 1425000, and the expenditure is 970,000. So, we will have 455,000 as the net profit in this case. Now, the next question is, can we kind of plan it better if we have a way to work around with these demands and do it? Very simple terms, if instead of 2,500, 3,000 and 4,000, which adds up to 9,500, if the demand itself were 3,200, 3,200 and 3,100, we know for sure that the cost will come down, because the amount of the overtime would be distributed here, it will be distributed a little bit here, and then the inventory cost can be saved. The 500 that we used for overtime will be distributed in evenly, but the cost will be the same, but the inventory cost will come down, therefore, the total cost will come down and the total profit will go up. But what organizations try and do is also to have different ways by which they can actually adjust this demand. Now, that is called demand planning. And how do they do that? They do that by giving some price discounts. So, when price discounts are given in certain periods, say particularly during the lean period, the off season discounts are given. So, when off season discounts are given, the demand which is going to happen later in a peak period is going to be spread out evenly, so that the demand during the lean period also goes up. So, the peak demand will come down, but the demand gets spread out, but the total demand also increases a little bit because of the discount that is given. So, if we look at a situation where now after say an off season discount, the demands for the periods become 4,000, 4,500 and 4,000, if this is the demand that is given. So, now what we will do is, we will produce 3,000 regular time in each of these, we will produce 500 overtime in each of these, and then we will have to do outsourcing. So, 3,500, 500 outsourced, 1,000 outsourced and 500 outsourced. So, total cost will be, regular time cost will be 900,000, total overtime cost will be 1,500 into 120, 180,000. If the outsourcing cost happens to be say 130, then we have 2,000 into 130, which is 260,000, which gives us a total cost of 1,340,000 or 13,40,000 as the total cost, as against 970,000 here. The reason being the demand is now higher. Now, we have to look at the profit. Now, when we worked out the profit, here we said that the total cost is 150. Let us say we give a discount and the total cost becomes rupees 145. Then the total money will be 145 multiplied by total demand is 13,500, which gives us 1957,500 and 134,000, which gives us 517,500 as the net profit compared to 455,000. Now, a quick look at these, one will be first tempted to say that this is excellent, mainly because the profit has gone up, but then we also understand the profit went up not because we only spread the demand, but we also increased the demand as a result of this discount of 5 that is given. So, there is some kind of a loss because the 150 has become 145, but unless the organization is able to increase the demand, number one, as well as spread the demand, if the organization is able to do these two things by offering this discount, then it is profitable for the organization to do this. But on the other hand, if the demand, total demand is near about 9,500, say 10,000 is the total demand instead of 12,500. So, the total cost will be 12,500 into 145, let me do that, which is 1812,500. So, this is 1812,500. Yeah, 472,500 is the net profit, which is still more than the 455,000 that we had here. Now, the organization should be able to, it has brought down the cost or price by 145 by giving a 5 rupee discount on this. Now, if the 5 rupee discount is adequately compensated by two things, one is a spread and balance in the demand, and the other is the increase in demand. So, if we are not able to get that increase of 3,000, then it will not be profitable to give this discount. So, two things have to happen. What is the extent of discount that is given? When is the discount given? So, these two things are important. So, the discount is given particularly during the lean period, so that the demand can be brought forward from the peak to the lean. The peak would always mean that we have to increase the capacity, which means the cost will go up. In these calculations, we have assumed that this 3,000 is intact. Sometimes the regular time capacity also can be increased by increasing the workforce. So, the cost will go up. So, if we are able to bring the demand, the peak demand, and evenly distribute it, particularly through the lean periods, it becomes advantageous for the organization to do this and even gain a little bit of profit if the net demand goes up because of the discount. Now, this is an important aspect which is called demand planning, and this is something that organizations now have started looking at. So, it is actually profitable for an organization to give an off season discount, provided the demand for the period increases because of the discount and the peak demand gets averaged over certain periods. So, these are some of the aspects that one looks at, particularly when one does aggregate planning. So, if we go back to one of the earlier lectures where we looked at the various topics in production planning and control, we said we would start with forecasting, where we would look at forecast of the demand, where we answered the question how much is the demand that we have to produce and meet. Then we answered the next question in aggregate planning, where Now, if this is the demand that we have to produce and meet, how are we going to do it in terms of regular time capacity? Should it be fixed? Can it vary with the workforce? Overtime capacity? What are the other strategies? Is there an outsourcing strategy? What are the other strategies? Are we going to hold inventory, or are we going to incur some back ordering? So, we looked at all those questions. So, the decision that comes out of the aggregate planning takes input from forecasting, and the output from the aggregate planning are essentially the PT and sometimes WT. WT is the workforce in terms of man hours that I am going to employ. More importantly, PT as the number of man hours of production that we are going to employ. Now, we need to actually do two things. One is, how is this PT, the number of hours of production, going to be distributed into three things: regular time, overtime, outsourcing, which the aggregate planning has already done. And let us say we are going to use this many hours of regular time, this many hours of overtime. Now, how are we going to use these hours to produce the various products? Which product is going to be produced first? What is the order in which we produce these products? Now, that is answered in what is called disaggregation, sometimes called master production scheduling. Now, after we answer this disaggregation, then we need, here at this point we are going to say that, well, this product is going to be made in the next 2 periods. So, we also try and find out when these products are going to be made. Now, after we answer that question, or sometimes even parallelly, what are all the things that we make, individual quantities of each of these final products, and then each of these final products has its own set of assemblies and sub assemblies and bought out components. So, if a certain number of final products are to be made, what is the corresponding number of the bought out items that we should have? Now, that is answered by what is called the bill of material, as well as by what is called MRP, materials requirement planning, which tells us if we are going to produce and meet the demand for this many quantity of each of the products, what are the corresponding bought out items and in what quantities they are demanded or required, and then how are we going to manage our material or inventory buying policies for these items. So, that leads us to another topic called inventory management, which we will see in the next lecture. And after we study inventory management, we will go back and look at disaggregation, and then we look at MRP, and then after the MRP is studied and the inventory management is covered, we will then move into production control, which is sequencing and scheduling.